This is part one of two parts on how to solve projectile problems. Okay, and the way I'm going to approach this is just by solving a sample problem. Let's take a situation where we have level ground. They're not always level ground, but this first one is. Okay, and let's say that there's a football player who kicks a football at an angle of 30 degrees above the level ground. Draw that. And he kicks it at a starting velocity of 30 meters per second. That would be the starting speed. And the thing about projectile problems is we're going to assume, for the most part, we're going to assume that there's no friction, no air resistance, no friction. Okay, so what are we going to assume? No friction, no air resistance. We're also going to assume the only force acting on a projectile is gravity. So only force is gravity, and so it would experience acceleration in only the vertical direction of 9.8 meters per second squared. Since there's no air resistance or air friction, there'd be no acceleration in the x direction. So these are the things we're going to assume here. Okay, if it's level ground, which this is, we can assume that this is a symmetrical path that it's going to take. It's going to take a parabolic path, and it'll be symmetrical. So halfway along the journey, since this is level ground, the first half of the journey would be equal in shape, let's say, to the second half of the journey. So we could even split a problem up sometimes in half and do it that way. We also want to remember that the velocity in the y direction at the peak is equal to 0. Okay, so those are some of the assumptions we're going to make. Now what kind of question do we want to solve for? Well, let's say we want to find out what the range is, and we also want to find the total time in the air. Okay, so we want to find t, total time, and we want to find range. A symbol for range, since it's the horizontal displacement from the beginning to the end, that would be delta x. So that's the range. Okay, so let's proceed to do the problem now. Remember, we need to know our Galilean equations, so I'll just jot some of them down. So V2 equals V1 plus AT. We also know delta x equals V1t plus 1/2 AT squared, and we also know that V2 squared minus V1 squared equals 2a times delta x. So let's keep those in mind. Those are Galileo's equations, and we're going to have to use those. But we have to be sure that we're careful and use them either in the x direction or in the y direction. We're not going to mix apples and oranges here. Okay, you'll see what I mean. Alright, well, the first thing I would like to do is to take this vector of 30 meters per second at 30 degrees and split it up into components. So I want to get the x component, I can call that Vx1, and I also want the y component, Vy1. We need to find those. Okay, so let's go ahead and find Vx1. That's just the component. Vx1 would be equal to, just using trig, 30 meters per second times cosine of 30 degrees. Okay, and Vy1, this component here, is equal to the hypotenuse of 30 meters per second times the sine of 30 degrees. Now this one's easy. Sine 30 is a half of 30 is 15. So this y component is equal to 15 meters per second. Okay, and the x component I'll have to use a calculator on it. It's like 0.86 times 30, but let's see, 30 cosine times 30. I'm just using degree mode. I get about 26. So about 26. Notice I'm rounding roughly there, and that's fine to do here. So 26 meters per second for the horizontal component, and 15 meters per second for the vertical component of the starting velocity. Okay, so those are important because you see over here in Galileo's equations, we need what V1 is, but we need it in terms of the x direction or the y direction, not both at the same time. Okay, now what do we do? Well, one thing we can, by the way, this equation here, even though it says delta x, if we're using it for the y direction, that would become delta y, the vertical displacement, is equal to Vy1t plus 1/2 a sub y t squared. So this is all vertical information we'd have here. Okay? Now what is the overall displacement vertically? Let's look at this problem. It's on level ground. It's starting at this level and it's ending at the same level. So guess what? In this problem, the total displacement is 0, so I can substitute that right in here. What's Vy1? Vy1, we found out when we split this V1 into components, is equal to 15. And since it's pointing upward, I'm going to define that as positive. I'll just put a positive sign to remind you. 15 times t, and then plus, now 1/2, and what's the acceleration? The acceleration is gravity, right? in the y direction. And so since we're defining up as positive, that means that this gravity is pointing down. That would be a negative 9.8 there times t squared. Okay, so simplifying this, we get 15t minus 4.9 t squared equals 0. Okay, fine. Now what? Well, let's divide both sides by t, and we'll get what? We'll get 15 minus 4.9t still equals 0. So I'm dividing both sides by t. That'll eliminate you having to use a quadratic formula, right? And so then just simplifying it, we get 4.9t equals 15. Therefore, t equals 15 divided by 4.9. And that gives us 3.06 seconds, or about 3.1 seconds. So that's the total time in the air. Now remember, it's not totally realistic because we're assuming no air resistance and no friction. But so if there wasn't any air resistance or friction involved, it would stay up there quite a while, 3.1 second hang time for that football. Okay, now let's try to find the range, or delta x. Well, okay, let's go ahead and look at Galileo's equations again, and oh yeah, that looks pretty good too. There's a delta x. In this case, we can use it pretty much as is, so I'll bring that down here. And delta x equals Vx1t. We're just doing it for the x direction now, plus 1/2 acceleration in the x direction times t squared. But what is the acceleration in the x direction? There's no acceleration in the x direction, is there? Acceleration in the x direction is 0. So that means that's 0. Half times 0 times t squared is just 0. So that whole term drops off, and it just leaves us with this to find the range. Okay? So the range then would be equal to Vx1, which is, we found out earlier, 26 about meters per second. We just found over here the time was 3.1 seconds. We can multiply those two together, 26 times 3.1, and we get 80.6. Wow, that's quite a kick. 80.6 meters for the range. Okay, so this is the end of part 1. I'll see you guys when you start part 2. Thank you.